Hi, today we're going to look at the Raspberry Pi Model B Plus I/O capability, the GPIO, and what we're going to do is look at how easy it is to connect external devices up to extend its I/O capability, to do driving of relays and things like that, and also to hook up things like a digital to analog converter. We're going to cover things like SPI and I2C Bus, which are the two main serial buses that the Raspberry Pi has. Most embedded systems have them, and the Raspberry Pi is no different from that respect. We're also going to have a look at the built-in capabilities of a library that is available, that's been very well written, that has it's called a wiringpi, and it's encapsulated a lot of the work that you would have to do in order to be able to talk to the GPIO of the Raspberry Pi and any additional chips as well. There's quite a few libraries for existing devices already, and they seem to be growing at a reasonable pace. And what it basically does is allows you to program the Raspberry Pi's I/O in a very similar fashion as you do something like an Arduino Uno or other devices of that nature, even the launch pads with their wiring type of capability. So the syntax is pretty much the same. You obviously don't have a UI to write it in the same way, but you just compile it from the command line, but the structure is the same. So without messing around, let's go to the Pi and have a look at what's involved. So what I have here is a Raspberry Pi Model B Plus. It's just sitting in a plastic base container so it doesn't short out anything on the bench. And the only thing I've got hooked up to it right now is a power from my USB adapter to keep it powered up, and a network connection. So everything we're going to do today is going to be through the SSH connection, through the internet connection on this, through the house Wi-Fi. And the other things that I've got connected up here is two sets of I/O. At the top here, well, let's start off with power, I guess. You've got the brown wire and the yellow wire here. This is providing 3.3 volts to the devices I'm hooking up, and the yellow wire is providing a ground. The black and white wire here, which runs across, is the I2C bus that is one of the default connections from the Raspberry Pi. We're taking that across to the breadboard, and then at the bottom here we have a SPI connection. Now, SPI uses a lot more connections than an I2C, but it can run very, very fast as well. Anyway, what you've got is you've got a MISO, MOSI, a clock, and a chip select. So the MOSI is master out, slave in. So this is where the Raspberry Pi would be talking to external devices, and the MISO is the master in, slave out, which is the line that the slave devices talk back to the Raspberry Pi on. A clock signal is used to basically time the data going in and out of the chips, and then the chips themselves need a chip select line in this case, which is the fourth line for this. Now obviously I'm not counting the power lines, which would bring it up to 6. Now the other thing with the I2C, just flipping back to that for a second, is I2C does not have address lines or anything else, not in the sense of having a chip select that would allow the Raspberry Pi to control it. What these have instead is each chip and device that you put onto the I2C bus has internally programmed an address. So you would actually say, I want to talk to address 48, and here's what I want to say. And then you would finish that communications, and then if you were going to talk to a different device, maybe you would say, I'm going to talk to number 80, and here's the data for that. Or if you're talking to an analog to digital converter, you would tell it, device 80, start a conversion. Now device 80, tell me what your reading was. Now obviously I'm speaking in English with that regard. It's going to be binary commands and things that are going to be serially sent over the interface to the chips and things. Anyway, that's the Raspberry Pi. I will put up a schematic of what I'm using for this, and link in, of course, the libraries. I did not write the libraries, but I am using them, and I'm going to extend it over some future videos, not the libraries, but the use of the libraries, to start building up some useful functionality out of the Raspberry Pi and some external devices. So let's change the view and have a look at some of the two devices that we're going to play with today. So the first device that we're going to use here today is an I2C device, and it is a 4-channel 16-bit digital to analog converter. It's a DAC 8574, not to be confused with the port expander, which is also an 8574 designation. This one is specifically from Texas Instruments and is a digital to analog converter, and quite a reasonable one at that. So we're going to have a look at what it takes to get that up and running, and what kind of commands you would use to control it, and later on we'll also look at how you can integrate that with a C program. And then the other device that I have here is at the back on this other board, way at the back there, and this is it's a Microchip 23S17, and what this one is a SPI connected device, and it is a 16-port expander. So it's basically an I/O device, and you've got 16 pins out of the 24 that's on the chip that you can set to be any input, any output. You're able to control the pins on a pin-by-pin basis through the command, so you don't have to refresh the entire 16 bits every single time you talk to it. And it's got the capability of driving and syncing around about 25 milliamps max per pin, but the total chip doesn't allow you to do that. Just the max per pin is. So if you probably based it on 10 to 20 milliamps per pin for normal use, you'd probably be better off. Or if you're trying to drive any heavy loads, you would put a ULN2003 open collector Darlington driver or something, and have that power a bigger relay or something like that. In fact, if you look at the PIFace Digital boards, either the PIFace Digital 1 or the PIFace Digital 2, which is for the Raspberry Pi Bs, you'll see that that's exactly what that has on it. It has one of these chips, and then 8 of the pins are actually connected to a ULN2003, and then 2 of those pins go on and feed relays that are on the board, and the other ones go through to drive some LEDs and also out to some output pins for you to hook up your own devices to it. So anyway, we're not using the PIFace Digital in this experiment, although you could easily do it, and the libraries that we're going to be using do happily support the PIFace Digital and a few other things as well. We're just going to be talking straight to the chips, because you don't really know what you want to drive, and things like the PIFace Digital board are great for experimentation and everything, but at the end of the day, when you want to build something, maybe you're just talking to LEDs and things like that, and you don't need some of the functionality that's on one of those boards, and you want to maybe build your own little circuit up, or whether it be on a breadboard or whether it be for a fully designed PCB or something. But anyway, what I'm showing you is how to hook the chips actually up, rather than just buying a board ready done and just plonking it on the headers of the Raspberry Pi. So anyway, so what else have we got in here? Yeah, the cables coming off of the Raspberry Pi, let me just back the camera up a little bit. They all come to this header here. It's a convenient way that I've got. This was actually for the older Raspberry Pi B, not the B Plus, that had the smaller header on it. But it's got a little breakout that allows me to plug it into a breadboard, and I can use jumpers that have a socket on either end to make the connections easily. And then what I've done is I've used local jumpers with pins on to go to the various devices here. So some of these pop across to where I've got the I2C connected D2A converter here, and then the other ones jump across and connect the SPI connections across to this port expander over here. The other chips that are on here right now, this is a quad analog to digital converter, digital to analog converter, and I've got to design some software for that yet, so we're not going to be dealing with that today. We've got a voltage reference here, which is being used to supply a precision 5 volts to the digital to analog converter on this board, and the other chip here is actually a 24-bit analog to digital converter, which is also a SPI device, but I haven't hooked that in yet either because there's no libraries, and I need to write up some software to drive it properly first. If you are interested in that, I actually did have another video which was using a SAM-D24 board from Atmel that was talking to that, and the code is going to be very, very similar. I just haven't had a chance to verify it yet and get it working, so I'm not going to include it in this demonstration. Now, this Raspberry Pi that I've got, the B+, I actually set up a little while ago for the drivers and everything else. So I'm not going to take you through that on this one, but I am going to follow up with a similar video on the Raspberry Pi Model 2B. And in that one, what I'm going to do is take you right from having completed the Raspbian install. So from that point onwards, installing and enabling the SPI drivers and everything else in order to get this working. I won't repeat the piece that deals with talking to the devices, because that's going to be exactly the same on both counts, whether it be the B+ or the revision 2. So it'll just focus on getting the drivers up and running and everything else on the version 2. But for now, the key things here that you need to start on when you're trying to use the Raspberry Pi B or any of the drivers on a Linux machine is verifying that they're actually installed properly. So to that end, you have to there's some checks that you can do right off the bat. So the library that we're going to be using is the wiringpi, and it's been created by Gordon Henderson, and it's available for download straight from GitHub. So the first thing you're going to have to do, if you don't already have it on your Raspberry Pi, is download the Git core libraries that allows you to download it. It's actually, sorry, it's not on GitHub, it's actually on Gordon's own Git server. But so anyway, to load the Git software, you need to do sudo apt-get install git-core. Now I'm going to put all these instructions into the blog post anyway, so don't worry if you don't see them right here or can read them properly, but I'm putting them up on the screen. So the first thing you do is download the Git. Now I've already got it, but I'm just going to run through this again. I will do a much more detailed version of this later on, as I said, when I run through it on the Raspberry Pi version 2. The next thing you need to do now is download the wiring software. An important thing to remember too, before you start wondering why things may not be working, is before you get through to running everything, make sure you have your Raspberry Pi up to date with its own software. So do sudo apt-get update and follow it with a sudo apt-get upgrade. Let that complete all of the upgrades it needs to do, and then go on to start loading the drivers and everything. So to download the libraries, you go to get clone and then the address, which is on dragon.net, wiringpi, and press enter. Now I've already done this, so it may give me some errors or at least warnings of duplication here. Yeah, so I've already done this, so I will go through this again in detail, as I said, on my other video when I do the complete details. So I'll repeat these whole exercises for a Pi 2. So once you've downloaded it, go into the wiringpi folder that it would have created when you did the download, and then you need to run the build. And to do that, you simply do /build. And that's busy doing that now, and that's complete. Now I'd already done it, so it may have gone a little bit quicker this time around, but once you've done it, now you're able to start testing things. So one of the first things right off the bat to try is GPIO --v, and that'll tell you that the software is loaded. It also will report back what version of Raspberry Pi you have, which in this case is the Raspberry Pi B+ with 512 megs of memory, and it also is verifying that I'm running GPIO version 2.26, which is great. So it's telling me that the compiler has loaded everything up and things are basically working there. So the next thing to see is whether you have the SPI and the I2C drivers running properly. So for those, there's obviously the part where you've got to go into Raspberry config and turn them on. Assuming you've already done that, then what you would do is run some command line tools to see what happens. So another tool that's automatically there when you download and do the compilation is a GPIO read all command, and what this will do is it'll actually read all of the digital pins on the header of the Raspberry Pi and report their current status to you, which is what I've just done there. So that's pretty cool. It gives you an idea that everything is working and what things have been configured for, which, as you can see here, you've got your SPI connectivity here, you've got your I2C connectivity up here. So not only does it tell you how they've been configured at the moment, or but it also gives you the pin numbers for the 40-pin header as well, so that you can relate this to what you're having to plug your wires into on the actual Raspberry Pi. Okay, so how do you know you got the SPI drivers all up and running? If you run the command ls-l/dev/spy-dev* and it'll tell you if the drivers are loaded. So in my case right now they are. So you've got SPI-dev0.1 and SPI-dev0.2. That tells us that you've got basically two SPI devices available to you. And if you look on the Pi pinout connections, you'll see that there are two pins, 24 and I think 26 on the header, that are designated CE0 and CE1. These are the two chip enables for your SPI connected devices. The Raspberry Pi only comes with two out of the box by default, and the software will take advantage of these. If you want to have more, then you'll have to start talking to the SPI bus more directly, so that you can enable your own GPIO pins to use for the chip selects, because that was one of the differences between SPI and I2C, is that I2C devices, that you address them with a hexadecimal 8-bit, or sorry, 7-bit number, whereas for SPI devices they have no address, at least not externally anyway, and you have to use the chip select line to tell them which device you're going to be currently talking to, which means controlling a GPIO line first to say I want to talk to you, and then sending out the commands to the device. Now obviously the libraries hide a lot of that functionality from you, so you don't have to worry about it, in the same way as the Arduino libraries and things do it for you as well. But if you do want to extend beyond the standard two chip select lines that are provided for you, then you do have to start writing some libraries, or at least manipulating them using the SPI drivers directly rather than fixed device drivers. Now to clarify that though just slightly, the 16-port expander that we're actually going to be using today has 3 address pins on it as well. Now these are not for external addressing. As I said, with SPI you can't do that. What they are, they're for internal addressing. So you can have 8 of these 16-port expanders, which basically means, that's what, 8, 16, 128 I/O pins, with only using one chip select. And what happens here is that one of the first commands you send out to the chips is to use the internal addressing capability, and from that point on you can actually send a command out to all of them and specify which one you're about to talk to, and then you would send out the real command to that one to turn the I/O on and off and things like that. So that's quite a neat little feature, but not all SPI chips have that. Usually it comes in families of chips to allow you to be able to do it. So you'll just have to check the data sheets of whatever devices you're wanting to use at the time. Yeah, anyway, I digress. So what next? Yeah, so when you want to get the drivers all running with the GPIO library, then you need to do the GPIO load SPI. Very simple command. It doesn't give you any feedback. Now if you have an error here, that probably means that the SPI drivers aren't loaded. So the previous command we just did, where we listed the directory under dev SPI dev star, that would have not listed out the devices, and you may have to edit the blacklist.conf file and things, which I will go through, as I say, when I do the Raspberry Pi 2 video for doing all of this stuff. In the meantime, I've got this working, so the GPI load SPI worked quite happily. There's also one for I2C, just to load up the GPIO drivers. Again, no feedback or anything, and now we're ready to start testing a few things out. So while we're on the subject of I2C, there's a standard command called I2C detect, and the -y that you've got, that you can see on the screen right now, just says yes, don't bother prompting me for any warnings. And then the second parameter, which is a 0, tells me which bus to scan for I2C devices. So if I do this one right now, it's probably going to show that I've got nothing, because as I said, there's 2 SPI buses on the Raspberry Pi, but only one of them is brought out, and in this case it's the channel 1 that's board out onto the headers. In the older Raspberry Pis, 256 meg memory ones and things, this would have actually given you a list of devices, but they changed it when they upped the memory. So what we want to do is actually specify bus 1, and when we do this now, you can see here that we actually have a couple of devices showing up. Now the 48 is actually the address of the digital to analog converter, and I think the 4D is actually part of that as well. It's got again, this is another one of those I2C devices. It's got addresses, and you can actually gang some together and make them all listen at the same time on the same address and things like that, and then have internal addressing similar to what SPI devices can do. So I think that's why the 4D is there as well. If you want to uniquely address it, you can use 4D, and if you want to specify a group of them, you can use 48. I'm not going to go into the details of how the chip works, but I will show you it working in a moment, and actually getting it to output a voltage between 0 and 5 volts on 2 of the channels. Anywho, so now the next thing is, what can we do with the SPI devices? So we have, or I have a LED hooked up to one of the pins of the device. I've put it onto GPIO-A because it's got GPIO-A and B on the chip, and it's on the GPIO-A pin 7, which is the last pin because it starts with a 0. So how do you actually talk to that? Well, the first thing you've got to do is tell it to set the pin up as an output, and when you do that, you can also then subsequently start controlling it like any other GPIO pin on the Raspberry Pi, where you just you output to the file system a 0 or a 1 to turn the output pin on and off. So let's just see what the syntax of that looks like. All right, just clear the screen because it's getting a bit messy here. So the command that you need to do is the one that I'm showing you on the screen here right now. So everything starts out with GPIO. That basically gets you into the command line of the library. And then you need to specify what device you're using. And in our case, it's a SPI device, and it's an MCP23S17. As I said, same as what is being used on the PIFace Digitals, both the old one and the new one. So you can actually probably use the PIFace Digital scratch utility to actually control and look at the pins on this as well. You will be limited to the fact that you can only have the first 8 inputs and the second 8 as outputs, because it doesn't allow you to reconfigure it, but it still gives you a nice easy graphical to be able to play around with the device. Anyway, you've got the bus number. The way the GPIO works is that it assigns a generic bus base address for each of these devices that it puts in, and this one happens to be using 100. And a couple more parameters, trying to remember what they're for. Oh, the channel and things like that they're on as well. For the details of this, I will refer back to the data sheet, sorry, not the data sheet, but Gordon's installation and detailed documentation. He has a very, very extensive website that details all of this. So I'm not going to try and explain every nuance of what the command lines do. I'm just going to show you how to use it and get some devices working so that you can start playing around yourselves. You can do a lot of reading yourself, and as I said, I'll link in the URLs to all of Gordon's pages that'll help you read up on this. Anyway, the last 3 parts, which are really what's relevant here, is the mode, where we're setting, and we're setting the mode for 107. Now remember, I said that 100 was the base, so this is the 7th pin. Now it starts at 0, so it's the 8th pin on the chip, and I wanted to send it as an output. So when you just press enter, it just does that. Now it won't show you anything else because it's accepted it, there's no errors. Now the next thing to do here is to actually start writing values, and the commands for these are pretty much the same as any other basic commands that you would see in a sketch or something on an Arduino. Here we're doing it from a command line, so we're having to specify a lot more, but if you look at some of the C code, which I will be going through how to write some of the C code for this and showing you some of Gordon's examples as well and demonstrating them working, but for now we're just going to do it from the command line. You do a write, you tell it the port number, and you tell it whether you want it to be a 0 or a 1. So what I'm going to do is I'm just going to execute a output 1 first and then an output 0. So it's not going to come back with any status on the screen here or anything like that on the computer. So what I'm going to do is I'm going to turn around and focus on the LED, which is at the back here. If I can find it. Typical, all the wiring happens to be in the way. I got all the meters hooked up for other experiments as we go through this. So there we go. There's the LED that I've hooked up to pin 7 on port A of the device. So if I output a 1 to it, and there you go, it comes on. Now I'm just going to press up arrow on the screen and change it to be a 0, and I'm turning it off. So now obviously any device that you then want to subsequently connect to this, all right, you can amplify that logic 0 and 1. Remember, all this is only using 3.3 volts at the moment. That won't really drive a lot, except it will drive a transistor that can then subsequently drive a relay that can then subsequently drive pretty much anything you want, depending on what kind of relay you give to it. So in this case, I'm driving this little LED, but you know, opto isolator would be another LED, and then whatever you put on the other side of it can be all sorts of different things. On the PIFace Digital, there are some relays and things that are being driven, but they're using the ULN2003, which is a great little chip with a whole set of Darlington drivers in it that can drive about 600 milliamps per pin. So if you want to start driving some bigger loads, that would be the device to look for, or you just start using some MOSFETs or something like that, which I've done in plenty of my other videos of how to drive MOSFETs and everything else, high side, low side, using Darlington drivers, opto isolators, everything else. Just look through my videos on YouTube and you'll find those. The very fact that I'm using a Raspberry Pi to drive this and turn these I/O pins on and off is really irrelevant as far as how you drive power devices from a logic level device like the expander, or even from the Raspberry Pi itself. So have a look at those videos if you want to do that for yourself, and experiment away. Just be careful though, if you're going to do mains, make sure you're either qualified or you have somebody to help you, because I will not be responsible for you electrocuting yourself. All right, so I think that's pretty much as far as a SPI-based device is concerned. There's really not much else I can show you there at the moment. When I do get it back on the computer to show you some of the code and do a sketch, you'll see how these things communicate. And if you go look on Wikipedia under SPI, S-P-I, then there's a whole description on how SPI works and everything else. I just want to show you what's involved to get it running on the Raspberry Pi. So now let's have a look at some I2C stuff. All right, now again, the Raspberry Pi has 2 I2C buses on it as well. One of them is always brought out in the connectors. One of the other ones is shared with a whole bunch of other GPIO. So it's not normally enabled or anything, but the driver is still there. And it's just like you did with the SPI devices, you can actually do a scan of, unlike with the SPI devices, you can't scan for all of the SPI addresses without toggling all the potential chip select lines to see if anything is there. With I2C, you can actually try and address all of the different chips that might be on a bus, and you don't even have to tell them a command, because the very fact that you address them will force them to send back a acknowledge bit where it just pulls a line down for a second just to say, oh, I'm here, I'm listening. And so by doing a scan across the bus and listening for that as you go through each address, you're actually able to build up a map. Now if I run this command right now with bus 0, you'll see that it's not actually showing me anything at all. And remember, I ran that before, and I did it with a 1 subsequently to that, and showed us the devices that are on here. So there's the device that we're interested in. It's on hex port 48, and the next step, of course, is how do we talk to it. So what I have here is a data sheet. I'm just going to very quickly bring it up. So the device we're using is a Texas Instruments DAC 8574, and as you can see here from the specs, it can work on anything from 2.7 volts to 5.5. Now I'm running it on 5 volts because I have a 5 volt reference as well, and obviously you know, if you are running on a 3.3 volt supply, then you won't be able to use a 5 volt reference with it. You would actually damage it. So the device itself is actually being powered from 5 volts, even though the I2C bus that's talking to it is actually running on 3.3. but the threshold tolerances for the I/O are wide enough that it will actually quite happily respond and not do any damage to the Raspberry Pi or be damaged, by itself. Obviously it's not going to get damaged by itself because with 3.3 volts, but it will respond and respect the communications protocols well enough still. So that's good. And what can this thing do? Well, it's got four outputs. So there's got buffers, digital analog converter, and you've got the outputs here that you can set any value. It's 16-bit, as I said, so you can set any that value between 0 and Vref. So in this case, I've got a precision 5-volt reference being hooked up to it, and it just used 2 lines. Again, this is one that's got A0, A1, A2, and A3. The first two, A0 and A1, allow you to put up to 4 devices with a base address on the bus. Remember I was saying that some of the SPI devices, you can do this where they're all sharing the same chip select, but you can actually treat them as individual devices. Well, I2C is naturally addressable devices on just 2 wires anyway, but which is these first A0, A1 can set the base. There's a base address, and then you can extend it beyond that with A0 and A1. And then the other 2 address lines, A2 and A3, allow you to internally set a separate device address. So you can have basically 4 of these all on the exact same address, which would give you 16 analog outputs on one address. And then of course you've got 4 separate addresses to play with as well, which now extends the whole range to have 64 analog outputs from just using many of these devices all put on the same bus without using too many external addresses either, which is pretty cool. Anyway, this is just a little device that it's a really tiny chip. I've put it onto a header so that I can plug it into my breadboard, and I fed it for a 5-volt reference from a Ref 02, which is another Texas Instruments chip, which is provides a very nice stable 5-volt reference, but it does need a 12-volt supply or a higher than 5-volt supply anyway to be able to do that. So I've also got 12 volts floating around on this board, which is why I'm being careful not to plug things in the wrong way, because if I put that 12 volts on the wrong device, I'm going to blow up my Pi and I'm going to blow up all of my 5-volt logic as well. So yeah, when you're doing this, beware. Now, like a lot of digital to analog converters, and also correspondingly analog to digital converters, they have internal references, and you can feed it from an external reference as well. Now the key with any voltage reference, of course, is not that it is accurate particularly, but that it is stable over time. That's both through temperature changes, through power supply changes, and through aging, and maybe that it's immune to noise. And as long as all of that is in play, then because you're using a microcontroller or a microprocessor to control the device, you can offset any errors in accuracy simply by using software. So it's not important that these devices these days are super accurate. Like even a voltage reference, you need to have it as 5 volts. Well, it really doesn't have to be 5.0000000, lots of zeros, volts accurate. It could actually be 4.98, 5.02, anything roughly around where you want it to be, because if it's stable, you can adjust what your readings are giving you through calibration in software and compensate completely for any inaccuracies. You just can't compensate for instability. So yeah, anyway, I think that's enough of looking at this. I will link in the data sheet for the package as well in the post when I put it up on YouTube. But for now, let's go and see if we can send this thing some commands. Alright, so the commands actually to talk to the I2C from the command line are pretty simple, and they're fairly standard across most Linux distributions that are there. You use the I2C set -y to confirm that yes, you want it. Then you specify the bus number, which in our case is 1. Then you specify the address of the device that you're talking to. Now remember, the 48 that we saw before, it's hex, so you precede the number with an OX to signify that it's hex, and then you output the value that you want to give to it. Now because this is 16-bit, we're going to output a word, so we're outputting FFFF. Now based on the fact that we're supposed to have a 5-volt reference, and the fact that it's supposed to be FFFF is all ones for the D to A converter, we should get about 5 volts out of this thing. And then the W at the end here is simply to tell it that we are outputting a word value. So now let's swing the camera over to the multimeter. I'm not going to bother showing you the device because it's not going to do anything when you look at it. But I do have some multimeters set up here. So the first two are connected to the first two outputs of the D-to-A converter, and the last one here I'm just going to show you the voltage reference just so you get an idea of what we're dealing with. Okay, this is the voltage reference that we're using to feed the D-to-A converter. So 4.999 basically. So that's close enough to 5 for what we need, and that should get reflected in the output of the D-to-A converter when we set it to full scale. Alright, let's bring the other 2 meters up. There we go. So what I'm going to do first of all is I'm going to set, like I showed you, the FFFF, which should set the first one to be 5 volts. And I've just put it in, and it's showing 5.004. So the D-to-A converter is running on a 5-volt rail for its main supply, and it's got an amplifier buffer on its output. So obviously the amplifier's buffer is not exactly following what the VREF max is, but that's okay. Like I said, you can compensate for these things in software. It is a 16-bit digital to analog converter, but as I said, I haven't bothered trying to trim everything right now, and it's running on a breadboard too, so you know there's a lot of things that can be affecting the quality of the output on this at the moment. But for what we're doing, that's good enough. So let me just change this to now output 50%. So I'm going to output now 8,000. Now there's something I want to actually quickly show you. I'll come back to the screen in a second. Is on here on the screen. Let's just let that get focused. Okay, man, focus. There we go. So it's a little quirk of talking to SPI devices, well, any devices serially basically. What I did, the first one is FFFF, which gave us the 5 volts. Now this one, it's not FFFF because I obviously want to do half volts. Now normally you would expect to see 8000, not 0080. But what happens here when you send this, the byte order gets rearranged through the SPI bus. So the lowest bit is going first, and then the high bit, right, as it's going serially into the chip. So you know, in some cases, if you're not getting what you expect out of it, just think to yourself, oh, maybe I've got the bytes swapped, and just tweak them around and try it again. And if that works for you, then obviously that's your problem. Not all devices are high byte first or low byte first, so you have to check the data sheets. In this case, I have to output 0080 to get 50% rail. So let's just flip back to the meters. And okay, so I'm going to output that now, and down to 2.5 volts. And just for the heck of it, I'll go to 4,000, so that's going to be 1.25 roughly. And now I'll go down to 0, which, okay, so there's a slight offset on there which hasn't, you know, which would need to be taken care of. That's a 0 bias. Now you should be able to get that down to completely 0, but like I said, it's on a breadboard and various other things, and there's lots of different stuff getting hooked up, so it could be having a little bit of interference there. But that's something again that you can tweak with your, there's some offset adjustments and things like that that you can do with the analog circuitry to compensate for that. Anyway, that's 0 right up through till 5. Now what do you do to do the other device in this case? You basically go to a different address. The least significant bit does not control the channel that you're using. The bit 1 and bit 2 actually allow you to address the various registers. So 10 is telling it to use the external voltage reference with channel 0. 12 would tell it to use channel 1. 14 would be channel 2, and 16 would be channel 3. So in order to output to the second channel here now, what I need to do is output to to 12, and then give it my requisite value. So it's going to output 50% right now. Let's see what happens. There you go. So up to 2.509, let's output full scale and see how it compares. FFFF. There's 5 volts, so it's just auto-ranging. And I find the Agilent 1273A rather slow to update compared to the 1272, probably because of the OLED display and things. A little bit annoying at times when you want to get instant gratification of an output, but hey, it works well enough aside from that, and it's very accurate. So let's go to 25% of range. That should be 1.25 volts roughly, so 1.26. And now we'll set it back to 0. So a similar offset on the output of that. I'll have to look into why that's happening, but I'm sure it's probably because of the breadboarding and various other things. Now what I'll do is I'll output this one at 50%, and I'll output the other channel at 3.75, which it is. So there you go. Now you've got the Raspberry Pi, at least from the command line. Now, if obviously the fact that you can do it in the command line, all of you Python aficionados out there will be jumping for joy now, because you're going to be able to easily output analog voltages, control digital I/O lines. You know, if you haven't already figured it out, now you can see how easy it is to do this with a Raspberry Pi with just a couple of basic chips, and now you've got 16 I/O lines, and you've got a digital to analog converter working. Now, the complexities of getting an analog to digital converter working is no different than what I've just done to show you the digital to analog converter. The only difference is you're going to be reading instead of writing. And when we get the Raspberry Pi Model 2 up and running, I'll actually hook up a couple of extra devices as well, and we'll do some analog inputs as well as analog outputs. And that's about it, I think, for now. So cover through that. Hope you like it. Give it a thumbs up if you do. Provide feedback if there's anything else I/O-wise that you might want to see with these, and I'll see what I can do to put them together. I will be having some videos as well extending from here. Obviously, this is just using a couple of chips on some breadboard, but I've also got things like temperature sensors, you know, like little Texas Instruments ones and things where you use one wire to communicate with them. And I've also got some NTC industrial temperature sensors and other things that I'll hook up just for fun as well, that I've got to use with a review for some industrial controllers. But because they are just resistance, you know, as long as you can put a current through them, then you can make a reading off of them to get the voltages and be able to convert that into an absolute temperature. So anyway, that's it for this one. As I said, give it a thumbs up if you like it, and watch out for the one coming real soon for the Pi 2.